So this video doesn't really correspond to any of the sections in Milne, but I want to give a brief review of field theory, the highlight being basically understanding what it means for a field extension to be separable, so that we can prove essentially the last proposition about tensor products in Milne in the preliminaries from commutative algebra chapter. So first, I'm going to start it off real basic, tell you what a field is. So recall a field is a non-zero commutative ring in which every non-zero element is invertible. Okay, so this is what a field is. Tell you what field extensions are. Let's say little k and big K are fields. And let's say I've got little k is contained in big K as a subring. So they have the same 0 and the same unit. And we call K a field extension. We call big K a field extension of little k. And we call little k a subfield of big K. Field extension of little k. Okay. So field extensions turn out to have a lot more structure than typical subrings. If little k inside of k is a field extension, then we can naturally give big K the structure of a little k vector space. The dimension is called the degree of the field extension. The dimension little k big K is the degree of the field extension. This is typically denoted big K colon little k. And if this dimension is finite, so if the degree is finite, then we call this a finite field extension. Okay, we say k, then we say big K is a finite extension. Little k. Okay. So this is some of the basic vocabulary of fields. The main thing I need to tell you about is what it means for a field extension to be separable. So hopefully this should all be review, but yeah, I guess that's the full thought. Hopefully this should all be review. So I'm going to let little k be in big K, be an extension of fields. So First, to define separability of fields, I need to tell you what it means for a polynomial to be separable, and then I need to tell you what it means for an element to be separable. Okay, so we say a polynomial is separable, so an irreducible f in little k of x is separable if it has distinct roots in the algebraic closure. Little k bar. An element, so maybe if I were going to be more complete, I'd tell you what the algebraic closure is. Essentially, all you really need to know about the algebraic closure is it's the smallest field over which all polynomials factor into linear terms. And I guess you should also know that they always exist. An element alpha and k is separable over little k if the minimal polynomial of alpha over k is separable. The minimal polynomial of alpha over little k is separable. Okay, finally, big K is a separable extension of little k if every element of big K is separable over little k. Okay. So essentially what I'm saying here is that big K is separable over little k if the minimal polynomial of any guy in big K has distinct roots in the algebraic closure. So there's a remark here which, well, basically says that everybody you know and love, for the most part, is a separable field extension. Any extension in characteristic 0 is separable in any extension of finite fields. Any finite extension of finite fields is also separable. So the two main classes of fields that you interact with are, you always get separable extensions. That isn't to say that non-separable extensions don't appear. They do, but less frequently. So in any finite extension of finite fields. Separable. Okay, so inseparability is a fairly rare condition that crops up in some places. So the next thing I want to talk about is the theorem of the primitive element, which turns out to be a fairly important theorem that I'm not going to prove. So I'm going to let little k and big K, this is going to be an extension of fields. We say alpha and big K is primitive for the extension sometimes we'll denote the extension by a little like fraction. This does not mean quotient is primitive for the extension. This is big K over little k, so not a quotient. Say alpha and k is primitive for the extension if all I have to do to get big K is join alpha to little k. And the theorem of the primitive element says that a lot of times your field extensions look like this. So theorem, this is called the theorem of the primitive element. It's kind of a cool name. It says let big K over little k be a finite separable extension then for some alpha and k big K, we have big K equals little k join alpha. Okay. So there's so essentially one way to view this is as a classification theorem for finite separable extensions of fields. It says that, remember, k. One way to write this remark. Recall k join alpha is little k join x mod the minimal polynomial for alpha over little k. So this theorem says that finite separable extensions always look like this for some alpha. So this is kind of cool. Okay. The reason I really wanted to talk about this was to prove this theorem in Milne. Which looks like the following. So there's quite a few hypotheses. So k is going to be a finite separable extension of little k. And omega is going to be some crazy big field extension of little k. So the typical place you want to think of this, well, it may not make sense yet, but maybe you want to think of omega as R or C, or where we'll apply this a lot is actually with omega being the p-adic numbers, okay, and little k being q, and maybe k being a number field. But for now, omega is just going to be an arbitrary field extension of little k. Okay, and essentially the theorem tells me the structure of the tensor product here. Then k tensor over little k with omega. So notice these are both, since they're both extensions of little k, they're both little k modules, or equivalently little k vector spaces, so this tensor product totally makes sense, is a product of finite separable extensions of omega. And it looks like this. So k tensor of a little k with omega equals 1 to r omega sub I. Okay. And we'll see in the proof that, yeah, I guess maybe the statement even continues. I can say a little bit more about these factors omega sub I and their relationship to k. So if alpha is a primitive element for the extension, is big K over little k, then the image of alpha tensor 1 in omega sub I, so I would pass through this isomorphism alpha tensor 1 and then project down omega sub I is a primitive element for omega sub I over omega. Furthermore, ff and let's say fi are the minimal polynomials let's say f is the minimal polynomial of alpha over k and alpha I over omega, then f factors as this product f sub I of x. Okay. So essentially the way the proof goes, so just to give you an idea before we actually get started on it, is I write k as, I use the primitive element theorem to write k as some quotient of k join x. I look at what happens when I tensor with this field extension. It turns out essentially that this k becomes an omega, and then when I factor this thing, I can use the Chinese remainder theorem to break this quotient into a product of quotients, each of which will be an omega sub I. Okay, so let's go ahead and do the proof. If alpha, so I'm going to start with a primitive element say alpha for the extension big K over little k. So this exists by the primitive element theorem. Big K is a finite separable extension of little k. Then, basically by this remark, we have this k equals k join alpha, which is k of x mod the ideal generated by f of x, where f of x is the minimal polynomial of alpha over little k. So essentially what I'm going to do is consider the following sequence of isomorphisms. Big K tensor over little k with omega. This is isomorphic to, I'm going to call this isomorphism phi. This is isomorphic to k join x mod f of x tensor omega. Okay, and this map here is bar phi tensor ID, and you can check that this is in fact an isomorphism. Okay, and furthermore, this is isomorphic to. The second map is a little bit more complicated, or like maybe not more complicated, but the second map sends a little g of x plus this ideal f of x tensor a little omega. Yeah, maybe it's a little bit more work to check this is an isomorphism, but you can do it maybe by defining a map the other way. That's probably how I would do it. Yeah, in general, it's really hard. In general, it's really hard to check that a map out of a tensor product is injective. So when you're trying to show you have an isomorphism between a tensor product and some other module, it's really helpful to define an inverse going the opposite way generally. Okay. So this is the map. Essentially, what you do is you just multiply by omega in the in this guy and take the quotient. Okay. So we've got this sequence of isomorphisms. What we're going to do is we're going to factor f over this larger ring omega. So suppose f factors now. As, let's say, I equals 1 to r, f sub I over omega sub x, or over omega join x. So this is where the separable hypothesis comes in. Since alpha is separable over k, this means that f of x is separable, which means that none of these factors repeat. So if we just think about this for a second, if I had two of these same fi's, well, these same fi's have the same exact roots over the algebraic closure k bar. That would mean that at least one root of f is repeated, which would contradict the separability. Okay. So each fi must be distinct by the Chinese remainder theorem. So this big family, so essentially all these ideals are coprime, so each ideal f sub I guess maybe the family of ideals, the collection, are pairwise coprime. So by the Chinese remainder theorem, So starting with this thing, big K tensor K, we saw above that this is isomorphic to this quotient, which if I factor f over omega, this is isomorphic to f1. It's the product, modulo the product of all these ideals, fr, should be an r. Okay, and then by the Chinese remainder theorem, I can split this up into a bunch of products. And each of these guys are going to be my finite separable extensions of omega f sub r. Okay. So I'm going to let omega sub I be these quotients, omega sub x mod sub I of x. Okay. These are each finite separable extensions of omega because the f sub I, f was separable, so each f sub I is separable. Since f was separable, each f sub I is. And so, yeah, there's like a lemma hiding in here, which I'm kind of glossing over, which says that if f is separable, if f is a separable polynomial, then like k adjoin x modulo f is a separable field extension. But that's true, so I'm not going to spend any time proving it. So each I is a finite separable extension of omega. And okay, essentially the result follows from here. So it follows. Okay, so let me look at each piece here of the result. Okay, so we definitely factor this thing as a product of finite separable extensions. If alpha were a primitive element, then the image of alpha tensor 1 in this guy is a primitive element for the omega sub i's. So let's think about this for a second. If I take my alpha and pass through this isomorphism, essentially my map is going to send like alpha is going to map to like x plus f of x, which is going to map to all these x plus fi of x, which do in fact generate the extensions omega sub I. And if I project onto the ith component, then this is just going to be x plus f sub I of x, which generates omega sub I over omega and has minimal polynomial. F sub I, so that f which is the minimal polynomial of alpha. I guess maybe I want to do this carefully. So that the minimal polynomial of alpha, which is f, which basically by definition factored as this over omega, which now we see is the product of these alpha i's, the minimal polynomials of these alpha i's over omega. Okay. So the proposition, we've proved the proposition, and it essentially tells us the structure of the tensor product of a finite separable extension and an arbitrary field extension. Okay, so this is the main result from this kind of field theory that we'll need. We'll kind of ramp up the field theory and the Galois theory as the quarter continues, and I'll probably try to maybe do, when we hit a big stretch of where we need a lot of Galois theory, I'll try to do maybe a lecture reviewing that. But for right now, this is all the field theory that we'll need. Okay, see you in the next lecture.